Example, the Brayton cycle with regeneration. The question states that a single-stage gas turbine engine with regeneration operates between 300 Kelvin and 1200 Kelvin. The gas enters the compressor inlet at 100 kPa with a pressure ratio across the compressor and turbine is 4. The efficiencies of the compressor and turbine are 80% and 90% respectively, and the effectiveness of the regenerator is 70%. Sketch the cycle on a TS diagram and determine backwork ratio, the mass flow rate of the gas if the power output is 100 MW, and the heat rejection to the atmosphere. Also, given to us are the value for the specific heat at constant pressure and the specific gas constant. If we draw the Brayton cycle with regeneration to the TS diagram, it will look like this. Please ensure that you know the condition for each state. For example, state 1 before entering the compressor, state 2 after leaving the compressor, and before entering the regenerator. State 5 is when the working fluid leaving the regenerator and before it enters the combustion chamber. State 3 is after the working fluid leaving the combustion chamber and before it enters the turbine. State 4 is when the working fluid exits the turbine and before it enters the regenerator. And state 6 is the state leaving the regenerator and before it being exhausted to the atmosphere. Next, we are going to list out all the information given from this question. The statement operates between 300 Kelvin and 1200 Kelvin is referring to the state 1 and state 3. Also given to us is the pressure at the compressor inlet P1 is equal to 100 kPa. The pressure ratio across the compressor and turbine is equal to 4. The isentropic efficiency for the compressor is 80% or 0.8. The isentropic efficiency for the turbine 90% or equal to 0.9, and the effectiveness of the regenerator is equal to 70%. Please ensure that you know how to find the isentropic efficiency for the compressor and turbine and also the effectiveness for the regenerator. Also, please ensure that you know what is actually really happens during these processes. Work in for the process 1 to 2, Q regen in for the process 2 to 5, Q in for the process 5 to 3, work out across the process 3 to 4, Q regen out for the process 4 to 6, and Q out for the process 6 to 1. Now, let's have a look at the items requested by the question. Backwork ratio can be determined by using the formula of BWR is equal to power in divided with power out. The mass flow rate of the gas if the power output is 100 MW can be determined by using the equation of power out is equal to m dot Cp times T3 minus T4. The heat rejection to the atmosphere in megawatt can be determined by using the equation of Q dot out is equal to m dot times Cp times T6 minus T1. If we look at the list of the equations to find the requested items by the questions, we need to find the value for the temperature for the state 1, state 2, state 3, state 4, and state 6. For state 1, the value for the temperature has been given from the question. T1 is equal to 300 Kelvin. In order for us to obtain the value for the temperature, for the state 2, we are going to use the isentropic relation between the temperature and pressure. Note that the pressure ratio is equal to the ratio between pressure at state 2 and state 1. The value that we obtain by using the isentropic relation is denoted by T2S. Since from the questions given to us is the isentropic efficiency for the compressor is equal to 80%, therefore we are going to use the value of 0.8 to find the actual temperature at state 2. The actual temperature at state 2 will be denoted as T2A. Once we substitute all the values and calculate, we are going to get the values for the T2A is equal to 482.3 Kelvin. For state 3, the temperature has been given from the questions, which is equal to 1200 Kelvin. For state 4, we are going to use the isentropic relation between the temperature and pressure to find the temperature at state 4. Note that P3 over P4 is equal to the pressure ratio. From the isentropic relation, we are going to get T4S is equal to 807.5 Kelvin. Given to us from the question is the isentropic efficiency for the turbine, which is 90%. Therefore, we are going to use the value for the isentropic efficiency for the turbine is equal to 0.9. By using the isentropic efficiency formula for the turbine, we can now determine the value for the actual temperature at state 4. Thus, we can obtain the value for the T4A is equal to 846.8 Kelvin. Let's assign Qregen in as Qregen and Qregen out as Qsaved. In order for us to find the temperature at state 6, we are going to use the relation of Qregen is equal to Qsaved. Therefore, in order for us to obtain the value for the T6, we first need to find the value for the T5. T5 can be determined by using the effectiveness of the regenerator, which is given by Qregen divided with Qregen max. Qregen max is equal to H5' minus H2. Since H5' is equal to H4, the Qregen max is now become H4 minus H2. The regenerator effectiveness that has been given to us is 70%. Therefore, we are going to use the value of 0.7. We will now substitute all the values and we can now determine the value for T5. Once you calculate it, you are going to get the value of T5 is equal to 737.5 Kelvin. Now we can determine the value of T6. The value of T6 will be equal to 591.6 Kelvin. Once we have all the temperatures values needed, now we can solve all the items requested by the question. Please bear in mind that we can use the isentropic relation for any isentropic processes.